Okay, so I think now we can start this session. Good evening, everyone. Welcome to the 11th live session of this NPTEL course in Machine Learning and Deep Learning, Fundamental and Applications. So in this particular week, we'll solve the week 10 quiz. So which was basically on artificial neural network. So we basically started with the basic notion of what is uh, the structure of a neuron, or so to say a perceptron. And followed by that, we have seen what is a multi-layer perceptron and etc. At the same time, we have seen that the training tricks, for example, backpropagation method over there. At the same time, we have also seen some of the other neural network architectures, and uh, we have also seen the paradigm of supervised learning, unsupervised learning, complete learning, etc. Now, in this particular week, as because the main focus was on the multi-layer perceptron, and subsequently in the week 11th content that is basically currently in the live position. So in that particular weekly session, CNN, you'll see that CNN or CNN based methods like VGG16, ResNet, and some of the other architectures, state of the art architectures, are also basically taught. So in this particular live session, I will be basically solving the week's quiz. However, in the next class, which is basically probably held uh, on tomorrow, so in the next class, we will basically try to see that how to simulate all these neural network architectures in Google Colab platform via uh, TensorFlow, PyTorch, etc. Because anyway, theoretical knowledge is important, that is for sure. But at the same time, these subjects are quite interdisciplinary and allied towards research. So therefore, you also have to know, you also should know that how to implement these methods on uh, in a real coding scenario. So now let us start solving the quiz. So the question states that which of the following is not a type of neural network architecture? So convolutional neural network. So convolutional neural network is a special case of artificial neural network. So that you will see in the week 11 content. So you start with a multi-layer perceptron, and the generalized version of a multi-layer perceptron where the weights are basically kept in a weight share manner. So there you will see that the convolutional neural network is basically a upgraded version of multi-layer perceptron. In case of multi-layer perceptron, the main point is basically the in the perceptron architecture, each and every node is connected with the each and every node in the previous layer is connected with all of the nodes in the next layer. However, in case of CNN or convolutional neural network, you will see that there is a weight share method is involved. Then long short-term memory. So long short-term memory is so is used for sequential data. Sequential data, which is basically time series type of data. Time series type of data. Now, the long short-term memory is also called another special type of neural network architecture, which basically comes under the head of recurrent neural network architecture. And if you see the architecture of the recurrent neural network, it is quite complex. So you have, uh, it is basically also based on the theory of causal data propagation. In simple terms, this means that prediction basically a function of current data and past information. So on this particular principle, this long short-term memory is actually based on. Then self-organizing map also you have seen this has a neural network architecture. It is a densely connected neural network architecture. So these all three um, varieties basically belong to the NN family. That is the neural network family. But this decision tree is not a neural network. In case of decision tree, you have the root node and you have the branches. And at the output, let's say these are the leaf nodes. So here you do the decision making. It may be either classification or it could be regression. So decision tree is not the neural network architecture. Yeah, Someshwar, I think he has some query.
Yeah, hi, good evening.
Yeah, good evening.
See, have we covered the question number one? Because there is, I had some query in that.
Yeah. I did not took the question number one because it is somehow incorrect. So I will
Correct, correct,
mail NPTEL first and then because there is some anomaly. So that is why I'm not solving
correct,
that.
correct. Because I took the derivative of that and I was not getting any
Yeah.
answer. So I
Yeah.
just selected some random also. Fortunately, it came correctly. But I know
Yeah.
that the correct option itself is not there actually.
Yeah, correct option is not there. Actually, correct option should be if you take in derivative in terms of x, matlab with respect to x, you'll get -1/3. With respect
Exactly,
to
exactly.
y, yeah.
I
So as
agree.
because the question is incorrect, I did not put it in the slide. I will
No
first mail
problem.
to NPTEL and then they will correct it and you will
Yeah,
get the
they should
marks
correct it. I
accordingly.
agree with you, and that's perfectly fine because that inverse
Yeah.
operation, what to take, that is not very clear actually. What to take with that
Yeah.
inverse operation? What did you
Yeah.
take when you calculated?
So it is like first you are doing x plus 1 and then you take inverse of this. That means 1/x plus 1.
Oh, one upon. So inverse means you are actually reciprocating it basically.
Yeah.
That's it, right? Okay.
Yeah.
Okay. All right. Yeah. Okay. Thank you.
Thank you. Okay, so the next question states that what is overfitting in the context of neural networks? So already we have seen that what overfitting means. For example, if we talk about a generic neural network architecture, it has certain limitations. For example, so in the x-axis, you describe the capacity of the model, or which is also commonly called as the complexity of the model. And in the y-axis, let's say you took loss as a performance measure of the model. So let's say uh, it is a regression task. So you have, let's say, certain data points and you have to fit a polynomial curve. So let's say the original polynomial curve is like this. And your neural network basically predicts something like this. So this blue one is NN prediction, and this green one is the original one. Now, what happens in case of uh, uh, if you train a model which is very less computationally complex? So for these models, you will basically learn something like this. Uh, you will learn something like this. So that means you can see it is not able to fit any of the data. So that means this particular pink line basically suggests less complex model learns nothing from the data, learns nothing from data. So this thing also refers to the term that is called underfitting. That means you're not able to learn anything from the data after basically training on that particular data set using the lower computationally complex model. But at the same time, if you train with a very complex model or a high capacity model, so what will happen? It will eventually fit each and every point, and it may learn something like this. So over here, you can see there is a steep jump is there. So it might learn something like this. And this is what you have seen in case of week one's lecture. If you just see the lecture again in week one, when regularization was taught, you will see the weight values. Certainly with high capacity model, the values of the weights were very high, and which basically creates some sort of jerk like this. So to reduce this sort of jerk for a high capacity model, we basically use the regularization techniques such that you do not see these sort of jerks or these sort of highly overfitted situations. Pretty fine. So, so this is what happens at the training time. So now you can see if you use a very high computationally complex model, so the model capacity is very high. So the model will very much the model will fit the data very well at the training time. So this also creates a problem. So this red one refers to certain points which can be highlighted as this is highly compute complex model. In training time, it fits the data very well, but in so in the training time, it fits the data very well. That means the training loss will be as minimum as possible. But in the case of unseen testing, unseen data based testing, model may show degraded performance. And one real life example could be, for example, if you are teaching mathematics to a kid, and let's say there are 3 to 4 exercises are there for a unit test, and uh, he has solved those 4 exercises 100 times. So by a natural human tendency is that if you solve something repetitively, the same thing, if you are solving that same thing repetitively, you will able to memorize that thing very well. Now the same thing happens in case of a high computationally complex model. So it basically tries to memorize the things rather than understanding the thing. Now what happens? Now the kid has solved that those particular 4 exercises 100 times. He has memorized everything, but in the at the time of examination, the questions that have came that are slightly different from the questions that are there in the exercise book. Now the kid will get hard time to solve those questions, and effectively in many of the cases, let's say the kid will answer something which is incorrect. So that means at the training time when you were teaching the kid, so that could be the training time of the kid. So at that time, with practice, which could be in analogy to the neural network with number of iteration or number of epochs, is basically with analogous to the times the kid basically practices the problems. So with practice, you will see the error will with practice error will initially he will do mistakes, so he will teach, and then with practice what will happen at the training time, the error will be significantly less. So that means the student is able to replicate those mathematical problems very well. But if the and so what happens, he will try to memorize the thing with a good amount of practice. Now if the question that have been asked in the examination, if they are slightly difficult or slightly different than what he has seen in the training time, he may perform miserably. Uh, uh, he may perform. Uh, he may not perform very much well in the examination. So that means at the time of testing, his performance will be degraded. That means he will do very high. He will incur very much of high error. So this refers that at test time, result is degraded. And as because I'm writing result is degraded, so it could be anything like loss could be increased. And if you are saying in terms of accuracy, accuracy will decrease. So the result is degraded and have high variance with respect to and have high variance with respect to training loss data. So you can see that at the time of training loss, the values were quite less. Now at the time of testing, the values are quite high. So the variance is quite high over here. From starting from this region to this region, you can see in general, the variance is quite high. So this is basically the zone of overfitting. So now let us scan through the options. What is overfitting in the context of neural networks? So when the variance of model is too high. Yeah. So this could be and candidate option. Now let us scan through the second option. When the model has too few layers. So now why I basically first try to discuss this particular plot. It is because you see in the option 2, it has been written when the model has too few layers. If you have few number of layers, that means the model is less complex. So at the time of less complex model, so which basically refers to this particular zone. So if you go along the x-axis, you will see the complexity increases, and high complexity refers to overfitting. And this is the zone which is basically the less complex part. So this is less complex part. And you can see at the time of with less complex model, which basically refers to this pink zone, your model is not able to learn anything from the data, which also refers to the fact of underfitting. So that means the analogy is less complex model have the analogy of underfitting, not overfitting. And high computational complex model, they have the analogy of overfitting. So therefore, when model has too few layer, it does not represent the overfitting condition. So therefore, this is not the correct option. When the activation function is not properly defined, activation function in general uh, uh, has no role on overfitting. It has certain uh, disadvantages which corresponds to overfitting, but in general, it is not directly related with the definition of activation function, whether it is properly defined or not. That has no role on overfitting, because you will see that I can show you in some in probably in later slides that with certain activation functions you might find overfitting issue, and with certain activation functions which have been proposed in recent years, they basically alleviate the issue of overfitting. So therefore, activation function definition cannot be the sole factor of overfitting. When the learning rate is too high. Now, when the learning rate is too high, for example, if your loss surface, let's say this is your loss surface, and this is where you do the initialization of the loss minimization problem. So this is loss, and this is with respect to the weight, which you basically update using gradient descent or backpropagation method. Now, if you have high learning rate, what will happen? You have to reach to this optimal position through optimization technique. This is the optimal position. If you have high learning rate, what will happen? You will end up at this particular position. Then you'll end up at this particular position here. Then again, you may end up at this particular position. So you will have lots of oscillations. So over here, you will have lots of oscillations before reaching the optimal position or optimal solution space. But this has no obligation in respect to the overfitting condition. You may reach the optimal solution. You may take much of time to reach to that optimal solution, but it has no relation with overfitting, because overfitting means that you are not you have learned the data very well, or you certainly have memorized the data very well. Therefore, at the test time, you have a high variance in the result. So therefore, this particular option is also incorrect. So high variance model basically refers to the overfitting condition. Okay. Next question states that what is the purpose of backpropagation in training a neural network architecture? Okay. So let's say you have a image of a person. You have a, let's say, image of a person and you have an image of a cat. So you have a data set. You have a data set D which has images that is xi and corresponding labels that is yi, and you have, let's say, n number of such images and labels. So this is image and this is labels of images. Fine. Now let's say you have a multi-layer perceptron neural network architecture. Let's say there are two hidden layers. This is the output layer. An output layer, node 1 will tell you that this is a human, and node 2 will tell you this is a cat. And at the input side, you will feed the images. And these are the connection of the weights. And as I have already told that each of the neuron in the next stage is connected with all of the other neurons in the previous stage. So you can see, so this is the neuron in jth layer and this is the previous layer I. So you can see this particular neuron is connected with all of the neurons from the previous layer. The same thing over here. And likewise, you can do this. Okay. Now let's say you have a situation, you have feed this particular image into this model and the weights. So let's say this is WJI, this is kth layer, and this is output layer, layer AL. Let's say this is layer L. So over here, the weights are represented as WKJ, and over here, the weights are represented as WL, K. That means WLK. Now, all these weights initially WJI, WKJ, WLK, these are randomly initialized. Sorry. There's some issue with the pen. So initially, these weights are randomly initialized. So you will feed the data and then you will subsequently do the forward pass. So this is called forward pass. And then at the output, you should get cat. And let's say, as because these weights are randomly initialized, these are not well tuned weight values, you do a you uh, do a substantial error while predicting this particular image. You know that the image should be labeled, the image should be predicted as cat, as because the ground truth label is cat. This is the true label, but the neural network prediction, let's say it is human. So that means you have done some error. So you have to calculate the error. And then based on this error, you will apply, you have to update these weights such that in the next iteration, when you feed the same image of this particular cat, you should do the correct prediction. So that means these things are called weight updation based on loss incurred. And how do you do the weight updation? That is using back propagation to gradient descent method. So at the time of uh, feeding the data through the neural network, so the pass that you do, that is called forward pass. And after you incur some loss, you have to backpropagate that loss to update these weight values. So that is called backpropagation or backward pass. So this is also called backward pass. And uh, the main objective of this backpropagation is basically to update the weights values such that you do the correct prediction. Because that is what your ultimate goal is. You start with a randomly initialized data, randomly initialized weight values in the neural network architecture, and subsequently with the number of epochs, you basically try to learn these uh, weight values such that you do the correct classification. So now let us scan through the solution. So what is the purpose of backpropagation in neural network? It is forward pass calculation. So forward pass is something else. In forward pass, what you do, you directly feed the data into the model and subsequently propagate from layer 1 to layer 2 to layer 3 to layer 4. So this is what forward pass means. It has no relation with backpropagation. So that means this is incorrect. Then calculating cost function. Calculating cost function means what? Error. And when you calculate error after forward pass, you check that whether you have uh, done the correct prediction or not. And if you have done misprediction, so then you have to calculate error. So that means in case of back propagation, so till this point, when you calculate the error, you have not reached the point of back propagating the loss value. So it is just after forward pass, you check that whether your prediction is correct or not. If it is not correct, then you calculate the error, or which is also called cost function. So that means it is also not involved with back propagation. Now, third point states that updates weights and biases on the predicted errors. So that means in the first what you have done, first you have fed the data, which is called forward pass, calculate loss, and third, what you do, based on loss, update weights through backpropagation, backprop. So this is the three key points that you have to remember that when you feed a data in a neural network architecture. This is the basic recipe. It is basically followed by each and every neural network, whether it is a multi-layer perceptron, CNN, whatever it is. So this is the third option is basically the correct option. Updating weights and biases based on the prediction errors. And regularization of the network. Regularization of network is basically uh, deals with reducing the overfitting of the model. In the last slide also I told that uh, over here when you hit overfitting, you basically your weight values basically increase rapidly. The weight value basically increase rapidly. So to limit those weight values, what we do, we use some sort of regularization technique such that you avoid those jerk based natures there. But it has no role with backpropagation because backpropagation is solely meant to update the weights so that you do the correct classification or correct prediction of the data. The next question states that you're using a sigmoid activation function in a neural network. If the neural network's weighted input is 2.5, then output of the sigmoid activation function should be what? So that means V is equals to 2.5. Now we have to calculate sigmoid of 2.5. So which is basically 1 divided by e to the power minus 2.5 and which is one divided by 1 plus e power minus 2.5, which is 0.92. Okay. Question 6 states that in a feed forward neural network. So you see the term is called feed forward neural network. Because why it is called feed forward? Because at the time of testing, at the time of training, you need to do the backpropagation. But when your model is trained, then what you will do? You will have an image and you just directly feed those images into the trained neural network architecture, and the pass that will do, it is basically a forward pass. You feed the data in the ith layer, then it subsequently go to jth layer, then kth layer, then lth layer, and at the lth layer it will do the classification. So that means at the time of testing, the pass that you will be doing, that is called the forward pass, and therefore the model is basically called feed forward neural network architecture. So the feed-forward neural network architecture has one hidden layer. Input layer has 10 neurons. 1, 2, 3, 10. Hidden layer has 5 neurons. And output layer has 3 neurons. Okay. Now, how many total weights of the neuron, including biases? This is very crucial that whenever in a question you see that including biases is there, you have to take care about the not only just W transpose X, you have to also take care about the B term or the W transpose X plus B term. So how to solve this particular problem is very easy, but just for clarity, let me draw the full diagram. So I will show it for a single neural network architecture, a single neuron, and then I will generalize the uh, thing. Now already we have told that this is input, this is hidden, and this is output. So already we know that uh, the neuron in the coming layer is connected with all other neurons from the previous layer. So therefore, I can connect all other neurons from the previous layer with this one. Right? So that means 7th, 8th, 9th all are connected with this particular neuron. So for this particular neuron, you can see that you will get W, H, I. So input is I and hidden is basically represented as H. So I can also specifically write it as W11, W12, W13, W14, W15, W16, and W1, 10. And at the same time, as because they have told that you have to include the bias as well. So you have a bias term as well, which is W1 naught. So at this particular neuron, what is happening is basically, so the equation will be, let's say your input is called X. So it would be W HI multiplied with XI. I ranges from 1 to 10 and plus this is where the bias term is basically coming. So the bias is what? W H naught. And as because we are talking about the first neuron in the hidden layer, so over here I can write H is equals to 1. So for this particular neuron only, how many weight values we require? Over here we need 10 weight values. Over here we need another weight value. So 10 plus 1 equals to 11. So for one neuron, we need uh, 11 of these weight values. So now I can generalize. So weight at WHI, so that means hidden to input is equals to hidden layer neuron multiplied with input layer neuron. This is for the weight part. plus hidden layer neuron. And this is for the bias term. So this is for the bias term and this is for the weight term. So I should write parameter. So parameter at hidden to input is basically hidden layer neuron into input layer neuron plus hidden layer neuron. So why this particular term is represented as bias term? Because you see, you have 1, 2, 3, 4, 5 neurons in the hidden layer. So for each hidden layer, you will have a single bias value. So in total, you will have 5 bias values, and which is basically the number of neurons in the hidden layer. So therefore, this represents the bias values, sum of all the bias values. And then the weights in this particular region, you know that this is also connected like this. So therefore, again, you will have this 10 cross 5 number of the matrix size would be 10 cross 5. So therefore, you can see that hidden layer neuron is 5, hidden layer neuron is 5, input layer neuron is 10, plus hidden layer neuron is 5, which basically now represents the bias term. So this is 55. So the parameter at WHI is 55. So from another analogy, I told you that for this particular term only, for this particular neuron only in the hidden layer, how many weight values or how in total, how many weight plus bias we need? So over here, we can see 10 weight values and 1 bias. So this is for a single neuron in hidden layer. So in total, we need 11 entries. So for one, if we need 11, we have 5 such neurons in the hidden layer. So 11 into 5. So 55 parameters. Now we have to also calculate in between hidden and output. So we have got the formula. So hidden output parameter is equals to, in output we have 3 nodes, in hidden we have 5 nodes, and we have to consider the bias as well. So for each of the neurons or nodes, we need 1, 1, 1 bias. So therefore, a total of 3 bias. So that means 15 plus 3 is 18. So the total number of parameter is basically 55. So total is equals to 55 plus 18. So that is 73. So this is the formula that you have to remember. Or you can intuitively answer as well. Okay. So in question 7, it is stated that consider a 3-layer backpropagation net with D input units and H hidden units and C output units and the corresponding biases as well. Find the expression of for output of node K. Okay. So let's say I have a neural network architecture like this. Let's say, suppose. So just for simplicity again, let me connect the neurons. So over here, let's say this is layer I. This is layer J, and this is layer K. And we need to consider the biases as well, as because in the question they have specifically mentioned. So let me write these things here. So you need to add bias as well. So this, in this direction you will get bias. So for each of the node you will have one bias, and over here also you will have bias. So this is for bias. So this is layer J and this is layer I. So how you will represent the weights? Weight is Ji. So you represent the nomenclature is like this. You have to write the upcoming layers notation and then the previous layers notation, that is Wji. Similarly over here the upcoming layer is K and the previous layer is J. So therefore you can write Wkj. And the biases you can write as because this is layer J. So Wj not, and over here this is would be Wk not. Okay. So now we have to comment about what is the output. So that is y. We have to comment about. So let us first see what is the output in general. What is the output at this layer I, or sorry, at this layer J? Output at layer J, and this is generalized. I will write generalized equation. You can also validate it for any of the neurons by putting the indexes properly. So let me write output of layer J is Yj is F. So this F basically represents the activation function. It could be sigmoid, it could be ReLU function, etc. etc. Tan H function. So sigmoid summation. So let us now talk about this particular neuron. So we already have seen how to write. So summation Wji multiplied with xi. So let's say your input is xi multiplied with xi. Yes. And then you have to add the bias. So your bias is what? wj naught, and I is varying from I equal to 1 to, so in the input layer we have d number of units, so it will vary from I equal to 1 to d, as because in the question they have mentioned that in the input layer, so this is also the input layer, we have d number of units. This is also referred as the hidden layer, and this is output layer. So this is the output of layer J or hidden layer. Now we have to predict what is the final output or output of final layer or layer K. So that I can write it as WO as well. Sorry, YO as well. So YO is basically, now it would be summation WKJ multiplied with YJ, because in feed forward neural network, what we do, we propagate the data in the subsequent layers. So this is basically the feed forward direction. So this is feed forward direction. So I can write WKJ multiplied with, or a dot product with, YI plus, we have to consider the biases in the last layer. So the bias in the last layer is what, how much? So that is WK naught. And over here, J is varying from what to what? J is varying from 1 to how many number of hidden units we have? That is H. So that means it would be H. And finally, I can also put a activation function on top of this before predicting the final output. So effectively, your functional representation can be written as summation J equal to 1 to H WKJ. Then again you can write f of WJI XI plus WJ naught plus WK. And over here, I is varying from 1 to D. So this is what basically your final composite equation will look like. So this part is coming from the hidden layer. And this whole thing is the output layer response. So now let us try to match with the solutions. So over here, they have not considered bias. So this option is incorrect. Fine. So we have considered that uh, layer K is the output layer, layer J is the hidden layer I is the input layer. So you can see all of them have written WK naught, WK naught, WK naught. So that means the last layer bias is correct for each and every case. Okay. Then here you can see that with this convention, if we follow this particular convention, because I, J, K we have considered sequentially, you can see the bias is WJ naught, WJ naught, WJ naught. So that means bias is also correct. Now let us see the weight values. So in the first case, we have WJI. So why J is initially kept over here? Because we have to write the subsequent layers index and then the previous layers index. So subsequent layer is J, previous layer is I. So WJI. So it is written Wji. Over here also Wji, over here Wij. So that means option C basically messes up at this particular position. So therefore option C is also incorrect. Now let us check about the last functionality, that is Wkj. So again subsequent layer is K. So that is why I have written K first, and the previous layer is J. So therefore J is in the second position. So it should be Wkj. So over here it is written that Ki. So that means it is incorrect. And over here it is written Wkj. So therefore this is the correct option. And this summation also, the first summation runs from j equal to 1 to h. Second summation runs from I equal to 1 to d. So that means this is the correct option. Yeah, Someshwar has some query, I think.
Yeah, hello. Can you hear me?
Yes, I can hear you.
Yeah, see, the whatever you explained is absolutely correct. Only problem with the options given, they
Yeah.
have given the summation outside and applied the function inside, which is incorrect actually. That f should
Yeah,
have been outside, which you have
yeah.
correctly wrote here.
This
Should be actually
this should
outside.
be this should be
Correct, correct,
outside. Yeah.
correct, correct. Yeah, but option that option itself is correct.
We do not make the questions. It is the
And I
TA from
understand.
the IIT Guwahati, they make the questions.
Yeah, yeah, no
So
problem.
they
No
they
problem.
must have done some
But
mistake.
we need to inform them, right? We can inform them that this
Yeah, yeah,
function
yeah,
should
yeah,
be
yeah.
outside. So that
Yeah,
next
this
time they will
function should
correct
be.
it, right?
Yes.
All right. Thank you. Bye.
Okay. Yeah. So the next question states that you are training a neural network using a fixed learning rate of 0.01. And after several epochs, you notice that loss is decreasing too slowly, indicating that learning rate is too small. So this is a very challenging problem in many of the neural network architecture. When you will train the model, so there is a optionality that is called learning rate scheduler. So what does this learning rate scheduler does? It adaptively changes the learning rate with the increase of epochs. Now, this has some uh, certain disadvantages as well, which is basically illustrated in this particular question. So you started training the neural network with certain learning rate, and as because you have kept a learning rate scheduler, it basically keeps on changing the learning rate with each epoch. There are certain other settings as well through which you can keep certain things that is called patience. That means from, let's say, if you keep patience equal to 10, so it will from iteration 1 to iteration 10, it will not change the learning rate. At the 11th iteration, it will change the learning rate based on the learning scheduler. So that is what patience basically means in the learning scheduler. So over here you can see the question states that you are training a neural network with a fixed learning rate. So that means the learning rate is 0.01. So eta is 0.01. After several epochs, so let's say this is your loss surface. So this is in y-axis you have loss, and in x-axis you have the weights. So with respect to weights, so if I just write the gradient descent equation, so you can see that is Wn equals to, I should write this arrow sign. So Wn plus 1 gets Wn minus eta into del L, which is loss, and you take the gradient of loss with respect to the weight, and N is the iteration. So let us consider you have a convex loss surface and you have a global minima over here. What you have to, what you want to achieve, because at this particular position, you get the lowest loss value. So that means your model will converge at that particular position. Your model should converge at that particular location. So you start your random initialization of weight. So let us consider this is W naught, random initialization at this particular position. And you have kept this learning rate value as 0.01. Let us consider this del L by del W is quite small value. Let's say which is also 0.002. So you can understand effectively this multiplication output will also be very small. So that means Wn plus 1, the equation initially what we were writing, that Wn plus 1 equal to Wn minus eta del L del W. So as because this value is almost approaching towards, so I can write it that the value approaches to 0. So I can neglect this particular term computationally. So Wn plus 1 effectively becomes Wn. So that means you can understand, due to very small value of learning rate, your progress is very, very small. So that means you will take subsequently large amount of time. So this is what I am drawing the iteration updates. So you start with this position, this position. So you will take large amount of time to reach this particular global meaning. So with very small eta, you converge very slowly. And at the same time, on the contrary, if you take very high value of eta, what will happen? It will do oscillations like this. So again, you will take much amount of time to reach at this particular position. So you have to use a very specific sort of eta value such that with significantly less amount of time you reach this particular global minimum position. So there are several sort of optimizers and other techniques are there through which we can achieve these uh, achieve these sort of responses along with the gradient descent method. So this is the vanilla gradient descent. Vanilla gradient descent means the standard gradient descent. So there are another techniques which are called momentum. So as the name suggests, even if you put very small value of learning rate, somehow mathematically it gives a momentum to the process. So therefore, instead of doing the small step updates with same learning rate within very small number of epoch, you will converge. So this is with this black curve is gradient descent. So with momentum. So there are numerous amount of techniques are there through which you can do. Very popular technique which came in 2019, that is called atom optimizer, which is adaptively which is adaptive momentum optimizer. So in neural network, if you see any sort of neural network simulation, you will see that many people uses this particular term atom, because it tries to convert the problem very fast. It tries to, in several cases, it fails also. So what should be the remedy? If you are using simple gradient descent, if you have put very small amount of uh, learning rate value, and you can see that you take a miserably high amount of time to reach the global minima, how you can tackle this problem? So you put a learning rate scheduler over there, and you try to increase the learning. Because if you increase the learning rate, then your step size will become high. So as far as this particular question is concerned, we have to see that we started with a low value, and for low value we require large amount of time to reach the global minima. So we have to increase the value of learning rate such that we can reach this particular position very fast. And as because uh, this is just a mathematical question, we just have to search which is the highest value. So over here we started with 0.01. We need to increase the learning rate. So over here, out of all these, so here you are decreasing the learning rate further. So therefore, it is not the correct answer. You have kept the same learning rate, because same learning rate will not help you. If you keep same learning rate, then again and again will take large amount of step to reach the global minima. So therefore, keeping same learning rate value will also not help you. So you need to increase the learning rate, and that is what we can see over here. 0.1. So that means when you increase the learning rate, it is likely to you reach the global minima in a less step, in less amount of steps. But let's say you increase this 0.1 to 1. So that means it is a very high learning rate, and therefore you will start getting this orange lines, or these are also called the uh, oscillations of convergence. So therefore, the 0.1 answer is the correct answer. And obviously, none is that you can merely discount. Okay. So I will solve the previous one, uh, this one later. So the last question states that suppose mean square error is used as a loss function. So MSE, so let's say you have y true and y predict, because you will be basically calculating the error between true value and the predicted value, which is basically predicted by the neural network architecture. So the mean basically 1 upon n. Let's say you have n number of true values and n number of predicted values. Then you will sum them for all the uh, errors. So it would be y true minus y pred whole square. So this is the squared error. This is the squared error part, and this is the mean part. Mean of the squared error. So that is why mean squared error. Okay. So in this particular question, they have stated that your model predicts a value. So a model predicts a single value. So that means your n is 1. And the predicted value, pred, is equals to 8 and target value. So target value is also basically refers the true value. So true is 10. So your MSE 10,8 is nothing but 1 upon 1. So summation has no meaning over here because you have single data only. And therefore 10 minus 8 ka square. So this is 4. Okay. Now let us solve this particular question. Just a moment. Okay. So there are some problems with this particular question is also there, but still let me just solve it. So again, I think I have to mail to NPTEL for this particular question as well. So let us solve this question. Yeah, I think Someshwar has some query.
Yeah, hi. Actually, I have addressed this problem and I got it correct. So what actually the question, there is ambiguity in the question. So it's not very clear what they want to ask us. So what I have inferred here is
Yeah.
that if your K, that is self-organizing map, if it is fed with those vectors, those are the input vectors like the 1
Hmm.
1 0 0,
Yeah.
0 0 0 1,
Yeah.
1 triple 0, and 0 0 1 1
On.
sequentially.
Okay.
Okay. So if we fed this K-Somas coherent organizing map with these input vector,
Hmm.
and the maximum cluster that we want to do it is M2, right? Two clusters
Yeah.
we want to
Yeah.
divide
Two
that
clusters
through.
we have to solve.
That's and the initial weights are already given to us in the format of this 0.3, 0.4, 0.6, 0.8, and the 0.7, 0.3, 0.6, and 0.3. These are initial weight matrix.
Yes.
And they have also given us the this alpha 0, which
Initial
is the
learning.
points initial learning rate. And if it goes to the next iteration, then alpha t plus 1 is also given. But the question itself is asking what is the weight after first iteration for
Yes.
this particular vector. So this will not be required. Alpha t plus 1 will not be
Yeah.
required.
This is
It will
not
remain
required.
only alpha 0.6 only what we have to use. That is
Yeah.
that information is redundant. It's not required. So
Hmm.
if we calculate using alpha 0.6 with this initial weight matrix
Hmm.
and input this input vector first, you have to input that. Then
Hmm.
second, what it will do basically after giving this input vector, it will determine the distance d1 and
Hmm.
d2
Hmm.
between the m1 and m2, and the
Yeah.
nearest one will be, let's say, in this particular case, the nearest one cluster will be
T2.
yeah, it's basically the in the first case the it will be neuron 2. So neuron 2 is the winning neuron because it has the lesser distance
Lesser
which we can
distance.
calculate using Euclidean distance,
Hmm.
and that's why we will go ahead using 0.6. We will update the weight of the second neuron. So basically that comes
That
to
means column 2.
correct. Column 2 is something which will update, and
Yeah.
then that that comes to after updation it comes to 0.88, 0.72, 0.24, and 0.12. That's the
Yeah.
second column. Yeah.
Yeah.
Then we go ahead in the next iteration. Means it's
Yeah.
the same iteration with the next input vector with
Hmm.
0, 0, 0, 1. Again, we
Hmm.
do the same calculation, and then
Hmm.
we determine using Euclidean distance that the winning neuron is number 1.
Number 1.
So we
Yes.
go ahead using the same 0.6, we go ahead and update the weight matrix, and that comes to 0.12, 0.16, 0.24, and
And
0.92. Then
yes.
in the third sequential vector comes to 1000, which is what is being asked here. And if we
Hmm.
give that as an input vector 1000, then the winning neuron comes again, winner neuron number 2. We go
Hmm.
ahead and update the weight matrix for that particular neuron, which comes to 0.952, 0.288, 0.096, 0.048. And fortunately, after this iteration, what are the weight matrix that we have matches with the second option. And that is how I have selected that particular option, and
So
it has come correct.
you have sequentially fed all these, right?
Just three of them because I already got the
Yeah.
answer, right? So fourth one is not
Yes.
required.
Yes. Yes.
Only after third, I am getting the answer which is matching with the second one. And that is what is being asked here. The first iteration, k-som to cluster vector this 1000, which is third.
Yes. Yes.
So after giving
Because the
that
question itself is ambiguous.
ambiguous,
Question.
you are absolutely
Yeah.
right. Question is ambiguous, but somehow that
So
answer has matched with,
many people will mark this particular thing as the correct.
and that is after second. This comes after
Yeah.
second
After second,
vector. Yeah, after second vector it comes,
they
but that
should
is
have
incorrect
told
option.
that the first iteration, that is also, they
That is
should have
also
clearly,
that
yeah,
they should clearly mention that this
clearly meant.
sequentially we have to input the vector, and what will be
Yes.
after third vector inputting what is that weight matrix is what you want,
Hmm. Hmm.
right? So that you are absolutely right. The question is really ambiguous, but
Huh.
this is how I addressed it, and
Yeah, yeah.
then
This is the correct.
finally it
This
matches
is
with
the
the
correct.
second one.
Yeah. This is the correct approach. So
Right.
as Someshwar already told that how we have to actually go along with the problem is that you can see that in the data set they have given the vectors in the vectors are 1100, 0010, and 1000, and subsequently there is another 10010. So sequentially, in any of the neural network architecture, for example, in the previous case as well, if I just show this particular diagram, so how we feed the data, that should be the first query. So we feed data sequentially. First, we feed a image of a cat. That means index one में जो data है that will feed. Then in the next iteration, we'll feed the index 2 data. So that means sequentially, we have to feed all the data. So if you see the question states that the first iteration for k-som to cluster vector 1000. So many people will do one thing, they will directly feed this particular thing, right? So if you directly feed 1000, eventually you end up with a incorrect solution. So how you have to do? So as Someshwar rightly pointed out, you have to start with this data, and subsequently you have to feed this. Then you have to update the weights that have been given over here. Then you have to feed this. Then you have to check what is the final update. Directly do not feed this particular data because as per the sequence given, it is at the third location. So first you have to feed this, then you have to feed this, then you have to feed this. And sequentially at each iteration, you have to change the you have to update the weight values as well. And as I have already discussed that what is the job of a learning rate scheduler, this is what is basically learning rate scheduler effectively looks like. So you can see alpha t will change at iteration 2, and the equation is given like this. So this is how in practice we change the uh, learning rate epoch by epoch. So as because this question is again itself a ambiguous question, I will just show you a method, show you the method that how you can address the problem. So you can follow the these steps for sequentially feeding the data, and you can get the answer uh, which is given as this particular 0.12, 0.952, this one. But the problem is quite tedious, so I am not going to do the whole solution. So I will just show you that uh, uh, how you can actually proceed with this problem. So at step one, take the first sequential data. So in our case, the first sequential data is 1100. Then step two, calculate the Euclidean distance from the given sequential data to the weight vector. And so over here, you have been given weight matrix, but I'm talking about weight vector. So we have to be specifically clear about what the weight vector basically suggests. So the weight vector basically says over here, you can see that your input data is 4-dimensional data. So I can write it as R 4 cross 1. R 4 cross 1 means real 4 cross 1. Even as because over here these are discretized data, so you can write Z 4 cross 1 as well. But R is the generalized representation as because the weights are real values. So weights are not discrete values. So I can choose real subspace without any problem. Okay, so we can calculate the distance between these and this. So this is the weight vector 1 and this is weight vector 2. Because for each of the data point, you need a weight vector. Because then only you will be able to do the matrix multiplication in case of SOM, in case of what you call the simple MLP and architecture also, you have seen that if you have n number of nodes, and that is basically connecting to the jth node of the next layer. So you have to have n number of weight values that you have seen from the previous parameter calculation method slide as well. So what I will do, I have to calculate D1 between, so the D1 basically suggests the Euclidean distance between weight vector 1. So let me just write it as weight vector 1 and let me write it as weight vector 2. So weight vector 1, 2, this data. So over here, let me name it as, let's say, A. A is basically my input data 1100. So I will calculate weight, which is Euclidean distance. That means I can write 1 minus 0.3 square, 1 minus 0.4 square, 0 minus 0 square, then 0 minus 0 square. And then again I can write D2, that is W2 comma A. And then again I can write the what you call Euclidean distance. So in this particular case, it would be 1 minus 0.7 ka square. Then, oh, sorry, over here it was 0.6 and it was 0.8. Sorry. And then I can write 1 minus 0.3 ka square, 0 minus 0.6 square, 0 minus 0.3 square. And then I have to check the least distance between D1 WA and D2 WA. If, let's say, so let me write say, if D2 WA, sorry, over here 1 and 2. So I might mess up with the notations, but the idea should be clear that D2 W2 comma A, let's say if it is less than D1 W1 comma A, then what it basically refers to, that we have to understand. So this means that W2 is best matching unit as it yields lowest distance value. So this is step 3. And step 4 would be whichever is found as the best matching unit, that has to be updated now. Now, the best matching unit has to be updated now. So in this case, we can update W2 would be updated. So therefore, I am writing a W2 star, which refers that it is updated. And how we can update? The update with the update rule. And the update rule would be W2 star is equals to W2. So this is the old W2 plus alpha naught, because your initial learning rate that have been given is alpha naught 0.6, and then A minus W2. So this is the equation that you can follow. And subsequently, you have to update this W2 star till you reach this particular data, because the question states that you have to see what would be the weight matrix after you basically feed this 1000. So they should have omitted this particular thing. So if they should have omitted this particular thing, people would have fed sequentially all the data and they would have reached the correct solution. So the question is quite ambiguous, as he has rightly pointed out, but you can follow this particular step, and then what you do from step 4 to step 2, repeat. Repeat in this particular case, I can write until reaches 1000. So you can do this at your own and then you can find the final answer. But anyway, I have to report this particular question as well as question 1 as question 1 too. So in the next week, probably by tomorrow as well. So, have you received any notification from NPTEL side whether there is any class uh, uh, scheduled tomorrow?
I think no, sir.
Let me check once whether they have mailed me or not.
It is there actually.
In the
There is no
website, they have.
email. There is no email, but if you go to the announcement tab
Oh,
in the course, we'll see the first message that week 12 content is live. And second message, which is actually sent today itself, 4th October, that dear learner, there will be a live interactive session on October 5th from 4 to 6. And there will be a session 2 from 6 to
yeah,
8.
yeah, yeah,
So
yeah,
it's there.
yeah, it's there. So tomorrow there will be another class. So on that particular class, I will solve some of the questions related to week 12. Let me see what is there in week 12. Uh, because I cannot solve the live quiz. Oh, sorry.
Week 11 is still pending, right?
Oh, yeah. Week 11 is still pending and the quiz is live as well, I think, right?
Yeah, quiz is live.
Due date is 10,
9th,
9,
9th
10,
October, yeah.
9th October. So I cannot solve this particular quiz directly, but I will take some sample questions which are related to this one. And then we'll also see that how to, we'll also see how to implement these VGG 16 or AlexNet, LeeNet, etc. In Google Colab platform because anyway, theoretical knowledge is very much important, that's for sure, but you should be able to implement these algorithms in uh, real life scenarios as well, in real life data sets as well. So we can have a hands-on session tomorrow.
Yeah, that will be good idea because as you rightly said, we cannot directly address this, right? The due date
Yeah.
is not there, so we can focus on doing some hands-on. That will be really great help.
So if you have any further query, then you can ask. Otherwise, we can end this session here.
Yeah, I don't have any query right now. If anybody else is there, they can ask. Otherwise, we can end.
Sir, I have one query.
Yeah.
Sir, which software is good for implementing this deep learning algorithm, whether Python or MATLAB? Because
Uh,
I have used MATLAB for
yeah.
implementing the algorithm I have proposed in my research.
Okay.
So I'm still a bit confused that which one is suitable for implementing
Yeah.
because
Yeah.
I am used to MATLAB. So I don't know
Okay.
whether Python is suitable or MATLAB is suitable.
Yeah. See, there are couple of problems with MATLAB. The problems are like in Python, it is purely open source platform. TensorFlow, Keras, PyTorch, these libraries effectively, these are open source libraries. And as because these are open source library, we have lots of contributors who basically contributes to build up the functions that we basically use. In case of MATLAB, if you see, I can show you just a moment. Uh, in MATLAB, there is a toolbox that have came probably in 2020 edition A, 2020 A. So that toolbox is called Deep Network Designer Toolbox, where you can actually uh, do the simulations of neural network architectures. But that so so is the screen visible, right?
Yes, sir. Yes.
So here, so this you can see deep network designer. So deep network designer, if you open, yeah. So when you open deep network designer, MATLAB has like they have given a, in one way you can say this is a good option. In another way, this is really somewhat bad, because if you do this, they have given drag and drop kind of functionality. So effectively, you do not have to write any code. So just you can connect them and create neural networks. So effectively, it seems very easy because you do not have to write any code. But this is detrimental in another aspect, because in MATLAB, if you see, they have in convolution part only, they have only 1, 2, 3, 4, 5, 6, 7, 8. Only 8 functionalities are there. But if you see, in contrary to MATLAB, if you see TensorFlow, PyTorch, and Keras, you will see whatever state of the art material is coming, all of them are included in Keras, PyTorch, TensorFlow, everything. But MATLAB, they do not update very frequently. So if you want to use any state of the art neural network architecture, very, I can surely say that you will not be able to you'll not be able to implement those things in MATLAB. So if you want to implement state of the art neural network architecture, my suggestion would be go for Python, because Python gives you a very wide realm of neural network optionalities. So over here you see hardly a total of 40 to 50 functions have been given. But in case of Python based libraries, there are plenty of such layers, such new architectures. Everything is basically provided there. So Python, as far as deep learning is concerned, so this is my categorical statement, but may not be like many people differs in that as well. So I specifically like MATLAB for signal processing task, because it gives you very good visualization, data visualization. But in case of Python, if you are solely working on deep learning uh, architecture, or you want to implement something on you want to implement some deep learning architecture, I specifically ask you to implement that in Python, because Python gives you way more flexibility than this one. And if you can scale up the models very well. In MATLAB, you cannot scale up models uh, very well, because these basically creates unidirectional and static computational structures. For example, I want to create two input neural network architecture. Till 2022, MATLAB did not support that functionality. But since the beginning of Keras and TensorFlow, they had that particular support. So this is where the problem lies. In MATLAB, they do not update these things very frequently, because in a calendar year, MATLAB basically gets updated 2 times, 20 A and B. But in Keras and in TensorFlow, PyTorch, and other libraries, Python-based libraries, you will see that collaborators and contributors update these libraries very frequently, such that you can have all possible optionalities. But in MATLAB, you will not see that. But for for beginners, you can use Visual Studio, then you don't have to write codes. But preferably, you try to learn Python.
Okay, sir. Thank you. Thank you.
Okay. Oh, Someshwar, I think he wants to say something.
Yeah. So thank you so much for that. It was really a wonderful session and wonderful insights about the comparison between MATLAB and the Python libraries. As you already rightly said, there are huge number of contributors as it is open source, right? Also, in
Yeah.
addition to that, Ushaji, Padmaji, how do you say? Yeah, Padmaji. So essentially, even if you see from a perspective of when you do a research, the fundamental component along with code is a data, right? A data set. And whatever the data sets which are available openly, freely, they have been mostly modeled using Python libraries. So that will also be very helpful if you go ahead with Python and use the available data set available in the market, even for learning also or for doing research also. The ready-made codes will be there in Python libraries already because somebody already tried that data set and they already have the data set as well as the code associated with that Python. Essentially, this Jupyter notebooks will be made available to you. So you can go ahead and straight away use it. But that won't be the case in case of MATLAB because it's been proprietary and as sir already told us that essentially it doesn't get updated also. So it really depends. If you are a starter as a beginner, go ahead and use MATLAB. If not, if you really want to go something do deeper, then you have to switch to Python today or tomorrow. That is my sense from my end.
Thank you for your suggestions, sir. Thank you very much.
Yeah, welcome.
Okay, so I think now we can stop the session then. Let me just stop recording.